Okay, this is the lab number 7. Modeling of registers. Modeling of registers. Okay. So in the last class, we have seen how to store 1 bit of data, right? Okay. By using the flip-flop, we are able to store 1 bit of data. Okay. So because why the memory elements are required, as we have seen previously also, whenever you are realizing the sequential circuits, definitely we want to store the output of the, we want to show somehow the output of the combinational circuit. Later, that output can be used in the combinational circuit. For that purpose, we want to use the storage elements. Okay. So far, we have seen only 1 bit storage element we have seen. Now we are going to store a set of bits. Okay. So we call it as registers are used to store multiple bits. Okay. Multiple bits, not a single bit. Okay. Multiple bits can be stored. Okay. So let us look at one important register that is called, okay. Let us look at the 4-bit register. 4-bit register. So what does it mean, 4-bit register? Which means we want to store 4 bits. We want to store 4-bit register. Okay. Right. Okay. But actually, of course, the main purpose of this register is storing the data, right? Okay. What are the block diagram for this one? For example, if this is your register, what is the size of the input? Size of the input must be 4 bits. Okay. 4 bits we have to apply as a DAN signal. Okay. And we want to get the 4-bit data as a D out signal or D out. Okay. Data in and data out. Okay. This data in must be stored here or not. That is decided by the clock signal. Okay. If there is a clock signal, and whenever there is a positive edge of the clock signal is there, then the data in will be transferred as a data out. Otherwise, the data must be stored in the register. Okay. Therefore, whenever there is a clock, whenever there is a positive edge of the clock, the data must be transparent. When there is no clock, then the data must be resides inside of the flip flop. Okay. Okay. Next, what we can see here, and of course, we would like to have one important global signal that is called a reset signal, RST. Okay. So we always prefer to use asynchronous reset. Okay. We always prefer to use asynchronous reset. That means first you have to clear the contents of all the register contents and then apply the clock and get the output. Output transparent or stored. Okay. So look at this one. What is the truth table for this one? The reset clock and D out, for example. Okay. So of course there should be D out also. Okay. Let me write the D out as well. So D in and D out. Okay. So this is what the truth table. So if the clock is available, okay, irrespective of the clock, sorry, if the reset is available, irrespective of the clock signal, I can say because it's a positive edge, right? Okay, whenever you see the positive edge of the reset signal, the clock is irrelevant and DN is also relevant. The output is D out, the previous value. Okay, whatever the previous, so I'm so sorry, it must be 0. What is this 0? 4 bit of 0. Okay, 4 bit of 0. Okay. Now, if the reset is not there, okay, if the reset is not there, when the clock is available at the positive edge, and whatever the DN we apply here, the DN will be transparent. Am I right? Okay. So for all other cases, if it is not there, okay, whatever the DN it is, it doesn't matter. Okay, the output value is D out. Okay, the previous value. So this is similar to that of a D flip flop that we have seen previously, right? Okay, just only the difference is that instead of the data in signal, we have to take 1 bit. Instead of 1 bit, we have to take 4 bits. That's it. Okay. Therefore, it's very simple to write a Verilog program for this. Okay. Let us go and write this. Let's start with module. Okay. By the way, okay, let me start in this way. Module, reg. Let me write in this way. If you write like this, it's very problematic. Reg, if you write like this, so should not write like this. Somehow we have to write addition 4 bit. Okay. What we can write? RST, clock, DAN, and DOut, right? That's what are the inputs here now? Inputs are reset, comma, clock or 1 bit size. Whereas another input is there, that is 4 bit size, right? 3 down to 0 of DA. Okay. Next, output is what is the output? Output register data type we have, right? That is also 3 down to 0 of D out, because we would like to write it in behavioral model. Okay, we have to write it in behavioral model. Right. Next, what is the question? What we have to write? Which statement I have to write? Always. Always at the rate of. So the output is changed on positive job reset, comma, positive job clock. Positive job clock. Project job reset and project job clock. Okay. Next, what if this is the case? What has to happen? Let's start begin. What we need to write? If reset is true, what about Q? 4 bit of, okay, not D out, right? D out is equal 4 bits of all zeros. Okay. 4 bits, all 4 bits are 0. Else D out is equal to D out. Okay. As simple as that. Okay. Let me write this is a and module. If this point is clear to everyone, right? A simple, just a simple, just like it's D flip flop, but we have used this thing. For example, I want to modify a small thing here. Okay. But whenever you are talking about the multi-bit storage, okay, we are going to use one extra signal called load signal. Okay. Most of the cases, registers use the load signal. That means whenever the load signal is there, then only the data in must go as a data out. Okay. If the load signal is not there, don't allow the DN signal as a D out signal. Okay, we don't want to transfer the data without having the load signal. Okay. So what modifications that we can do here? What modification we can do? Orbit register with load signal. What I have to add? So by using the one enable, it's just like an enable signal, single bit enable signal. Okay, LD. LD stands for load signal. You can write anything, it doesn't matter. LD, a load signal. So what I have to do here now in this case? So we would like to do something here. We are going to add something. What is that? Load signal, LD. Okay. So if the reset is available, irrespective of anything here, then it is 0. If reset is not there, if the clock is there, okay. If the load signal is not there, for example, if the load signal is not there, for example, then what has to happen? Actually, the question is that we don't want to use any kind of data, okay? If this is the case, we have to use a D out signal. That means the previous value only I want to keep it, okay? Because the clock is there, at the instant of the clock, the reset, the load signal also should be there. At the first edge of the clock, the load signal is not there. We don't transfer the data, okay? Now, what kind of load signal it is? Asynchronous load signal or synchronous load signal? Is this a synchronous load signal or asynchronous load signal? It should be asynchronous, synchronous load signal, because clock edge is there, then only the load has an impact. If the clock signal is not there, the load signal does not have any impact, right? That's called it is a synchronization with the clock signal. That's what we have seen reset signal also. RST, if the clock edge is there and the reset signal is there, then it is called synchronous reset. If the clock is there, it doesn't matter if the reset is having the highest priority, it does not follow that RST. Even the clock is available or not, doesn't matter. Whenever the RST is there, then the output is defined, then it is called asynchronous, right? So that's what we can write. So therefore, the load signal, if the now the question is, if the load signal is there, sorry, if the clock is there and load signal also must be 1, okay, then the output should be DIN. Okay, if for other cases, if the load signal is not there and the load signal is also not there, irrespective of whatever it is, then they should be D out, the previous value. Okay, all right. So what modification that we can do here? Simply load signal we have to add. Okay, better I can add the load signal before the DN signal. Okay, let me add this is a LD. Okay, what is the modification the code? What modification that I have to do? It is synchronous with the clock. That's the reason why LD signal should not be there in the sensitivity list. It should be inside of the begin and end block. Where we have to write? We have to write one if else statement, right? We can write one if else statement. What is the if else statement here? If the reset is not there, if the reset is high, the output is 0. Else if the load signal is true, then D out is equal to DIN.
For all other cases, else condition, if you're not giving this one, if the RST is not there, if the load signal is not there, if the positive edge of the clock signal is not there, for every case is what it should be, the previous value. Did you catch this point? This is how we have to apply the load signal. Okay. Right. Okay. You may ask the questions are why you have written the code something like this. Already I have written the D flip-flop code previously. Why can't I use that D flip-flop and create a structural modeling? Okay. So let us see how to design the 4-bit register, and from that, how to write a Verilog program for it. Okay. Because I'm going to make use of the previous 1-bit, sorry, one bit D flip-flop. So the D flip-flop we have already written. Okay. Let me write a 4-bit register using structural modeling. 4-bit register using structural modeling. Okay. Now what I can do the structural modeling. So to store 1-bit data, what I have to use? 1 flip-flop is required. Am I right? To store 1-bit data, 1 flip-flop is required. To store 4 bits, 4 flip-flops are required, right? Did you catch this point? Do you understand? Yes. Okay. Right. So now what is the input here now? The input is, for example, for simplicity, I'm writing here is a D naught is one input. Okay. And it will produce Q naught as my output. Okay. D naught is my input, Q naught is my output. Okay. This is done. This is done by using the clock signal. When the transparency is existed, when there is a clock signal, and definitely there should be a reset signal. Okay. Forget about for the time being, just I'm not going to use the load signal. Okay. Simple. Without having a load, I'm writing this. Okay. Now, when there is a RST signal, this flip-flop will be 0. Okay. If the clock is available, then the D out will be go as a Q naught. Okay. Right. So this is the one flip-flop. But the same flip-flop, the 4 bits are required, right? 4 flip-flops are required. Another 3 I have written here. It's simply, I can write it in this way. This is the second bit, D1. This is called Q1. This is called G2. This is called Q2. This is called D3. This is called Q2. Am I right? So let me consider the DFF D flip-flop 0, D flip-flop 1, D flip-flop 2, and D flip-flop 3. Okay, 4 flip-flops I have taken. Okay, now every flip-flop needs a clock signal and reset signal, right? Therefore, I can extend the same clock signal and same thing will be connected to all these flip-flops, right? Okay, therefore that it is also requires clock and this thing. Okay, something like this. Okay, now what is this flip-flop is called actually? This also has got, so what is this register we can call it as? This is also called as parallel in, parallel out register. So can I say like this? It is a parallel in and parallel out. It's simply a parallel input and we take the parallel output. Okay, therefore this register is also called as parallel in, parallel out. Out resistor. Okay, so whatever the program that we have written previously, that is simply a parallel in, parallel out register. Okay, well, this is what the box consisting of. This is a what box consisting of. Okay, okay. What is the top level module for this one? Let me write it in this way quickly. Actually, D is one input. This is a 4-bit size. Q is my output. That is also 4-bit size. There should be a clock signal. There should be a reset signal. Are you getting this point? What is the inside of this one? The inside of this one is this block, right? Okay, therefore, if you want to write a program for this one, I have already written the D flip-flop. I can call 4 times. Are you getting the point? Okay. So where I have written the Verilog code for the D flip-flop, the last class, I guess. In this context, I have written somewhere. Latch flip-flop. This is a synchronous flip-flop. This is. Where is asynchronous reset flip-flop? This. I hope I have a. Here I have written, but unfortunately, the set is removed for the explanation purpose. I will have done this one. Okay, let me take this particular one. Let me call this 2 times. Okay. Unless otherwise, if you're not model this D flip-flop first, we are not able to write a Verilog code, right? Okay. Somehow I have done this one, but reset is also required, right? Okay, let me model a little bit modification of this code is required. This is called RST, something like this. And this is also RST. Okay. It doesn't matter. You write first word is RST clock. It doesn't matter. Something like this. And if RST is there, then we have to write. If reset is there, if RST is true, then what is this one? D out is equal to, what is the D out? 1 bit of 0. Okay. Else, we have to write this is in keywords, right? Else is a keyword. If is a keyword. If this is the case, D out is equal to D out. Okay, this is what we have written previously. You're going to use 4 times of this one. Okay. How can I write the 4 times here? Let me start the module. Okay, for this one, it is required, right? First of all, I want to take this particular as a main block. This is external view. And let me copy this and paste here, and accordingly, I want to write the top level. Okay. So what is the, how can we start this one? Module rich underscore 4-bit underscore SM. SM stands for structural modeling. What are the inputs here? D is my one input. Clock is one input. Reset is one input. Okay, better I want to write the reset first and then remaining things I will write it left next. Okay. First, let me write the reset. Next to clock. Next to D. Next to Q. Okay. What are the sizes of this one? Input, RST, clock. Next, another input is 3 down to 0. Very good. D. Next, what is the output? Do we need to write the output as a register data type? In the structural modeling, doesn't require. Okay, when you are writing the behavioral modeling, we have to write it as a output as a register data, but otherwise it's not required. Okay, let me write here is 3 down to 0 of Q. Okay, now we have to call this one. See, the naming here is RST clock D and Q we have written, but the naming for this one is RST clock is fine, but D and D out I have given there. Okay, but I have to modify this one. So therefore, positional, instead of writing the positional assignment, the formals and actuals methods that I will use, or otherwise dot notation I will use. Okay. So what is my code here actually? This is what I have to call. How many times? 4 times I have to call. Okay. So first one is I'm going to call this is, okay. So this is called D flip flop. I have written previously. Now, what is the name of this flip flop? Okay. DFF naught. That's what the instance name. Like Z0, Z1, Z2, Z3, I have written as DFF0. But you should not change this one. But it is as it is, what wherever we have model, the same name we have used. You should not change this one. But here you can write it whatever you want. Okay. Now, so what we have to write about the clock? Dot notation, I want to use it. Okay. What I have to use? I have written the clock here, right? Okay. Dot clock is available. But now what we have to do? The clock of DFF is connected to the clock of this particular module. Are you getting the point? Look at this one carefully. Okay. So what is this clock actually? CLK. This black CLK belongs to whom? D flip flop. The D flip flop. This CLK, red CLK belongs to what? Present 4-bit register related clock. Okay, that we have connected both. Okay. Now, what about the next one? The next one is actually the reset of the things we have to define. The reset of the D flip flop. The reset of D flip flop is connected to whom? The RST of the 4-bit register. Agreed? Okay. Next, the dot. What about the next one? The DAN. The DAN. The DAN of the D flip flop is connected to whom? Anyone? The DN input of the D flip flop is connected to D naught. Very good. Okay, but D naught we have to write it in this way. Vector notation we have written D of 0. This is how we need to write. Okay, because D is actually vector notation I have used. Okay, next. What is the next one? Dot D out of the D flip flop is connected to whom? Q naught. Very good. Q of 0. Right? And we have to take the. Is it point is clear to everyone? How to write the structural modeling for this? For example, if you're using the same thing, for example, here also you're using the D and the Q, we don't bother about to write the dot notation. Directly we can write it there. Okay, but usually this is a good practice actually, right? Because of this dot notation, wherever you write the position is not important for us. Okay, you can keep it. This one is the first place. This one is the last place. It doesn't matter at all. Okay, but whereas if you write the positional related assessment, then definitely we have to follow the same thing. Otherwise, you will get the error output. Okay, so better you have to follow this particular. Now, how many times I have to consider this? 4 times. So let me take this is a 4 times. Copy. I have taken 4 times. What modification I have to do? I want to remove this 1 and 2 because the same instance you should be. And where I have to change these things, I want to change, right? Okay, let me go and write the change of this thing. This is called 1, this is called 2, this is called 3. And this is 1, this is 1. This is 2, this is 2. This is 3, this is as simple as that. Okay, right by the finally and 1. Okay, which one you feel better? Behavioral modeling is better, or this structural modeling is better in this case? Behavioral modeling is very simple, right? It's straightforward. We don't bother about the internal circuitry. Okay, that is what the advantage of using the behavioral model. Okay, just if you know the input output behavior, you can simply write by using the procedural statements, right? Okay. But in the examination, how they are asking, based on that one only, you have to write it. If I ask you to write the structural modeling, if you write the behavioral modeling, you will get 0 marks. Okay, right. So sometimes it is not only sufficient. Okay, that means the resistor is not only belongs to parallel. Okay. Or otherwise, for example, if I want to use the load signal also, what you have to do? The structural modeling also, I want to use the load signal, for example. Then what you have to do? We have to add, of course, I'm so sorry. Here also I need to modify something, otherwise it will be wrong. What is the modification here? Clock signal also I need to write, right? Was it job? Reset signal. I forgot, right? The reset signal. Okay. Right. For example, how do we write the how can I add the load signal for the D flip-flop? The previous value, previously only. You write the load signal LD here. You write if reset signal is 0, that is 0. Else if load Q will be, sorry, D out is equal DAM. Okay, then we'll come here. You have to modify this one also. One load signal we need to add here. And then wherever the load is set, how they are connected to the load, that we have to. If this point is clear to everyone? So please take it as homework. Please try to add the load signal and write the structural modeling for it. Okay, please try to consider it as your homework. Right. Now, as we have seen that a register is not only for the purpose of parallel in, parallel out. Okay, parallel in and parallel out, or nothing but it is just like a storing actually. Just like a storing, but not only most of the cases it is most of the cases to perform some arithmetic operations we are going to use the registers. That means it is also possible to use shifting operation. Shifting. That means registers can also be used for the purpose of shifting. Okay, we can see something like this. For example, you take the 4-bit data here. Okay, let me take for the sake of time. For the sake of time utilization, I'm going to use the same module. Copy. I want to use it. Okay. Not only for the storing, shifting also can be done. Okay. So, but how can you do this one? The shifting means I should not use this parallel in, parallel, right? Parallel in should not be done. What I have to do here, I have to connect it with, first of all, I have only one input is connected here. That is called serial in. SI, we can call it as SI, serial in data. So this value is shifted to whom? To the succeeding stages. Okay, therefore they should not be parallel in, parallel out. Okay, simply connect this one to this one. Output of this one connected to this one. And therefore this will be the input and this will be the output. And this will be the input and this will be the output for this one. And this will be the input, this will be the output. This is called serial
out register, serial out data. Okay.
Now, what kind of shift register it is? What kind of shift register it is? It is starting from right to left. What it is? Shift left operation, shift right operation. It is a shift left operation. We are moving to left side. Okay, shift left operation. Before
this is called serial in, serial out, shift left operation.
Shift left operation is a shift left operation. We start from the right side. We are ending at the left side. That's why it is a shift left operation. Okay. This is the one thing. Okay. Next, we'll take another thing. Another type of a shift register. There is a possibility of shift right also. So what modification that I can do for the shift right operation? What should I do for the shift right operation? So now the direction is not this one in this way. Okay. So by the way, I want to write it as for the simplicity, I'm writing as a D input signal and Q input, Q output. Okay. D and Q. D and Q. These are all the input here, output purpose I'm writing here. Okay. But actually, these are nothing but DAN and D out. That's what I have written. But because of the space consumption, I'm writing the D and Q. Okay. Please remember this way. Okay. What is the shift left operation now? So shift right operation. Okay. So that means that the position should be D3 should be here only. Okay. But from this side to that side, I have to go. What I can do?
I'm fixing this value in this way. Okay. Therefore D3, Q3 here, Q2 here, Q1 here, Q0 here. Okay. Here, what is the, while shifting this one, what will happen? So this is actually the first flip flop will fill with SI. The second flip flop will come the Q0, and this is come here. The output of this one, the output of this one is come here in this way. Okay. But what else? What about this one? Shift
Right operation. This is a serial income here, and this is a Q3. This is a Q2. This is a Q1. Yeah, that is Q1. Okay, this is somehow we are able to get that one. What about this one?
What about that?
What about this?
I am not going to change anything about the position, right? This is the position. That means MSB to LSB only. Okay. Now what do I have to do? So, but inputs, where is the inputs here? This is the input. So this is the input is here, and Q is here. This is the output D, Q, D, Q, and D. What I have to do here? I have to connect the serial in here. Okay. Take the output and connect it as an input to this one. Is that right? Apply the serial in at the MSB and take the output and connect it to the preceding stage, not succeeding stage, preceding stage. Okay. Next, take the output of this one and connect it as an input here. Take this one and connect as an input here. And take this is my serial out. If this point is clear to everyone, that's what I've done here. Okay, explanation I've given there. So what this is called? Serial in, serial out, serial in, serial out, right shift register. This is a serial in, serial out, a register. Okay. So what is the block diagram for this one? I'll top level module for this, something like this. Okay. We have a data here is actually serial in. We have a data at the serial out. Okay. And this is called clock signal. This is called reset signal. Okay. So the question is, how many clock signals are required to send the serial in data and transferred as a serial out data? See, I'm not mentioning any kind of this is a 4-bit register, 5-bit register. Okay, how many clock signals? Okay, for the time being, let me answer it in this way. How many clock signals are required to do this operation for serial in and get the serial out? How many clock signals? Only one clock is sufficient. Okay, the moment if you apply the clock signal, all the 4 bits will be, 4 data inputs will be loaded and then get out of that one. Only one. But here, if it is a 4-bit serial in, 4-bit serial in, serial out, how many clocks are required? For one clock signal, if you apply, the first flip-flop will be transferred. And the second flip-flop, the second clock, second they will be transferred. Third, fourth, like this. Okay, 4 clocks are required for this. Serial in, serial out. That means it's depending upon the size of the serial in, serial out, whether it's a 4-bit or 5-bit or 6-bit or say 32-bit or whatever it is. Is this point is clear? Now another question is, how do we do the shift right and shift left at the same time? That means bidirectional shift register. That means the same shift register used one time as a right shift operator, one time as a left shift operator. Okay, what we can do? You take a shift register. Okay, then we have to perform this one. Look at this one. For example, if this D flip-flop and DFF of this one, you consider these two. What is the input for this one? This is sometimes it is a serial in. Okay, sometimes it is a Q of this one. Q0 of Q1 of this one will be an input. Okay, look at this one. So if we take one flip-flop here, what is the input of the D and what is the input of the D? One input is coming from serial in, one input is coming from Q0. Am I right? Is that point is clear? Now, what about this one, for example? What about the DFF 1? What should be this input? D and Q. What should be the input of the second flip-flop? As you can see, what is the things here? Q0 is one input. Next, this is a Q2 is one input, right? So that means we have to choose this one as Q1, and this is called Q2. Are the input for this. Similarly, for this one, what is the input here?
for this one, Q2 of the previous stage, and this is Q3. The last one, it is D, and this is Q. What should be this one? Q2. Sorry, what about this? I think it's wrong. This is Q1, right? Yeah, this is a Q1 has to come here. This is a Q1, right? This is a Q0, right?
No, not like that. See, look at this one. So this one, for this one, SI naught, then this is actually Q1. Okay. But what about this one? This is for, this will come here, right? The Q0 will come. Okay, I forgot. It's a mistake is actually, it's a Q0. It's a Q0. Let me take the different colors. Let me take uppers and lowers also will take differently so that we'll see. Okay. For the shift left operation, what should be this one? Serial in. Okay. This is called Q0. Okay. This is Q1. This is Q2. For the shift left, right, left operation. Whatever the shift right operation, it should be Q. This is where it is coming from input. Input coming from Q1. Input is coming from Q1. What about this one? But this flip flop, what input, where input is coming from? Q2.
Where the input is coming from here? Q3. Where another input is coming from here? Serial, right? It should be serial. This is what we can see, that this is input, one input is coming from serial in the case of the shift right operation. In case of shift left operation, it is coming from Q2.
Okay, and that's what we can see. Okay, now the question is that we want to operate only one shifting. Okay, the right shift operation you can do it, the left shift operation you have to do it. That means you have to choose only one input out of these two inputs as an output. Therefore, what is the device is required for this? If you have two inputs are there, at a time only one input has to go as an output, then what kind of device is required? Multiplexer is required. What is the size of the multiplexer in this case? 2 by 2 cross 1 multiplexer is enough. Okay, we are going to have one multiplexer here. Okay, we use one enable signal. Okay, this is called one enable signal. If enable signal is equal to 0, what is happening here? Let us assume that this is the first line, this is the second one. What should be this one? Shift left or shift right? Shift right. Let us assume the Q1 will come here. The first one is Q1, Q2, Q3, QS serial. If it is coming from what kind of shift is it is? Right shift operator. Okay, if enable is equal to 1, for example, then what it has to do? Shift left operation.
Shift left operation. Therefore, simply we can write one multiplexer here. Enable signal. Okay, for all these multiplexers having the same enable signal. Okay, we'll take the output here. We'll take the output at this point. Okay. This is what the output. We take the output here. Q0, Q1, Q2, and okay. If enable is equal to 0, it is acting as a shift right operator. If enable is equal to 1,
it is acting as a shift left operation. Whether we have a possibility that you can take the output at a single place or you can take at a multiple place also. Okay. If you take the output, for example, if you take the output here, for example, okay, then it is a simply serial in, serial out,
shift. What is this one? Shift left operator. Shift left operation. If you take a serial in, serial out, if you take the output at this place, for example, if you take the output at this place, for example, then what it is? Shift right operation. Okay. Then if you want to take the output at all the places, for example, you're applying the only single input and you're taking the output at all the places, for example, then what we can call this is serial in, parallel out. It is a serial in, parallel. Where you are taking the output is important also. Okay. You are taking a MSB దగ్గర అవుట్పుట్ తీసుకుంటున్నారా, LSB దగ్గర అవుట్పుట్ తీసుకుంటున్నారా, లేదు అన్నిటి దగ్గర అవుట్పుట్ తీసుకున్నారా, దాన్ని బట్టి మనం డిసైడ్. But it is a serial in only. Okay. It is simply a serial in because we cannot apply the multiple inputs at the same time. Okay. One input serial in, we are applying one place and that will be distributed in all the places. Whether it will be moving the right side or left side. Okay. So this is called bidirectional shift register. This is called bidirectional shift register. Okay. We stop here today. Actually, what we have to do is we have to try to write the Verilog program for all these things. Okay, please try to write the structural modeling for it. Okay, for all these three things, shift registers. Okay, serial, right shift operation, left shift operation, bidirectional. You have to write a structural modeling for this. Okay, and next I will talk about what is the behavioral modeling for this one, and how can we construct a universal shift register based on this. Okay, we stop here today.